Here's a strange thought. Imagine cursive G represents the collection of all possible groups. The set or collection of all possible groups. Any group you can think of is in cursive G. Kind of crazy to think about, huh? Well, makes sense if we're viewing set theory in terms of naive set theory, just saying sets are collections of things. I can certainly create a set then that contains all possible groups. Any group I can think of is in this set. And plenty of groups that I cannot think of is also in this set because I maybe don't know them. Okay. The concept of isomorphism and two groups being isomorphic, if there's an isomorphism between them, defines an equivalence relation on cursive G. Isomorphism defines an equivalence relation on G. We talked about equivalence relations back in chapter 0, and we applied them in thinking about modular arithmetic a bit. Here in chapter 6, and especially in chapters 7 and 9, equivalence relations are going to come back. So we want to start getting used to them again. So what do I mean? I mean the idea of two groups G and G bar being isomorphic if and only if there is an isomorphism from one to the other. We've already defined what isomorphism is. It's a one-to-one and onto function from the first group to the second group that's also operation preserving, i.e. phi is one-to-one onto and operation preserving, OP, that this definition of this relation between groups is an equivalence relation. So that technically needs proof. How do you prove it? Remember from back in chapter 0, there's 3 properties you have to prove, and they go in alphabetical order: reflexive, symmetric, and transitive, RST. Reflexive property would be then in this context, well, in the general context of equivalence relations, it'd be to show any element is equivalent to itself. So in this context, that would be to show any group is isomorphic to itself. How do you do that? How do you show any group is isomorphic to itself? We'd have to come up for an arbitrary group, let G be an arbitrary group. We'd have to come up with an isomorphism from G back to itself. Any ideas? Any bright ideas for what might be an isomorphism from G to itself? You're sort of hinting at it, epsilon, but what's epsilon? The identity, but what kind of identity? What is it? Is it the E in G? Is G isomorphic to itself? G's group, it's got an identity element. So do we somehow use the E and G to create this isomorphism? I think it probably is better to call it epsilon, because we could think of it as being a permutation. Yeah, it would be the identity permutation. Yes. Your instinct to call it epsilon was good. Let epsilon from G to G be defined by epsilon of little g equals little g for all little g and capital G. I could have written epsilon of x equals x for all x in capital G. It's mapping everything of G in G to itself. It's the identity mapping. Instead of epsilon, some mathematicians call it 1, not the number 1, but the mapping 1, identity. Or maybe ID as an abbreviation for identity. You'll see that kind of notation. But I think calling it epsilon is good here because it could be thought of as a permutation. It is a one-to-one and onto mapping. Is it really one-to-one and onto? Certainly it's onto. Given little g in capital G, what gets mapped to little g? Itself. And certainly it's one-to-one if epsilon of G1 equals epsilon of G2. If the outputs are the same, can I show the inputs are the same? Well, by the very definition of what epsilon is, that implies G1 equals G2. There's nothing much to do. It's definitely one-to-one and onto. Is it operation preserving? Epsilon of G1 times G2, by definition of the formula for epsilon, that's G1 times G2. And also by definition of the formula for epsilon, G1 is epsilon of G1 and G2 is epsilon of G2. Done. Yeah, it's definitely operation preserving as well. And the proof of these things is really as trivial as what I'm showing here. It's one of these things where it's like so trivial, it's confusing. You're not quite sure if it's really right, but it is. So the reflexive property is satisfied. Any group is isomorphic to itself. How about the symmetric property? Does, phrasing these things as questions, does G being isomorphic to G bar imply G bar is isomorphic to G? That was the problem you worked on here for 20 minutes or so. If there's an isomorphism from G to G bar, is there an isomorphism from G bar back to G? The candidate you would use is the inverse function of the isomorphism from G to G bar. This implies there exists a phi from G to G bar that's, once again, that is one-to-one onto and operation preserving. Does that fact imply there exists an isomorphism from G bar back to G? The only thing that makes sense to try is the inverse function. Certainly if phi is one-to-one and onto, it's got an inverse function. That was back in chapter 0. We proved that in class. Certainly if phi is one-to-one and onto, there is an inverse function. But is that inverse function one-to-one onto an operation preserving? That's what you had to prove. Is this one-to-one onto and operation preserving? Probably. Yeah, and the answer is yes, it is. How do you prove that? Well, let's start with the one-to-one. If phi inverse of, I'll call it A, equals phi inverse of B, where A and B are elements of G bar. It's good to keep track of that kind of thing. Those are elements of G bar. Sorry, that's a G bar there. Does that imply that A equals B? You can use fundamental properties of inverse functions here. You can, in particular, you can use the fact that when you compose phi with phi inverse, they undo each other. That's the key thing to use here. Effectively, apply phi to both sides. Plug in both sides into phi. Since phi and phi inverse are inverse functions, that implies A equals B, by definition of what an inverse function is. On to, given, say, C in G, does there exist, asking this as a question here, an A in G bar such that C equals phi inverse of A? Maybe I should have switched my lettering around and called that an A and that a C. since the original mapping is from G to G bar, and alphabetical order would go from left to right, but don't worry about it. So I'm asking as a question here. Maybe we do want to draw a blob picture though. There's G, here's G bar. We're given a C in G. Does there exist an A in G bar that gets mapped to C under phi inverse? Well, think about how inverse functions are defined. Phi inverse of some A would be the unique C over here that gets mapped to A, which will exist because phi is 1-to-1 and onto. What should we choose for C here? Oh, excuse me. What should we choose for A? How about phi of C? We're given C over here. How about letting A be phi of C? Yes. Let A equal phi of C. Then what can you say? Phi inverse of A equals, by definition of A, phi inverse of A of C, or phi of C. But once again, phi and phi inverse are inverse functions. They undo each other. That equals C. We're done. How about operation preserving? Probably we need to use the fact that phi and phi inverse are inverse functions. And probably, if you think about it, it should make some intuitive sense that the fact that phi is operation preserving is probably relevant. Probably we need to use the fact that phi itself is operation preserving. So what are we trying to do? Given, I'll phrase it as a question again, given A and B in, I'm talking about the inverse here, in G bar, does phi inverse of AB equal phi inverse of A times phi inverse of B? That's what I'm hoping is true, phrasing it as a question. Probably I need to use the fact that phi is operation preserving somehow, and again, that they're inverse functions of each other. So maybe what I should try is I should try applying phi to both of these things individually and see if I get the same thing. And if I do, that must mean these things are the same because phi itself is 1-to-1. Yeah, I think that's the best strategy. Phi of phi inverse of AB, by definition of inverse functions, is AB. And how about the other one? Phi of phi inverse of A times phi inverse of B. Here's where you use the fact that phi is operation preserving. That's phi of phi inverse of A times phi of phi inverse of B. That's phi being operation preserving. You need that somewhere. That's where you use it. Now use the fact that phi and phi inverse are inverse functions. This simplifies to A times B. These are simplifying to the same thing. Phi of this equals that, but phi of this also equals the same thing. In other words, these two things are the same. Now use the fact that phi is 1-to-1. You got the outputs being the same thing, therefore the inputs must be the same thing. And that's what we wanted to prove, that those are equal. Feels like just this, this super abstract game with symbols, right? Just pushing these symbols around. But there is deep meaning to this, okay? And it's got tons of applications in math. You could say this has got tons of applications outside of math too. In linear algebra, remember I've said vector space isomorphisms, which are linear transformations that are 1-to-1 and onto, are group isomorphisms. And certainly vector spaces have plenty of applications in real life. You've got your basic applications in matrix algebra, but you also have pretty advanced applications. Linear algebra is one of the most applied topics that there is. If you look in your linear algebra book, like at the very last chapter, you're going to see lots of applications. But we're not done in proving that being isomorphic is an equivalence relation yet. We've proved the reflexive property and the symmetric property. We've got the transitive property left. Transitive. If G is isomorphic to G bar, and G bar is isomorphic to, oh, what should I call it? How about G double bar? Does that imply that G is isomorphic to G double bar? Fun with bars. So what do we need to do here? G is isomorphic to G bar, so there's a phi from G to G bar that's an isomorphism. Let me denote that phi like this. Instead of putting phi here in a colon and then a G arrow G bar, let me put G arrow G bar and put the phi above the arrow. It's another common way to write that, to visualize it. It's supposed to be a G bar there. So I'm assuming G is isomorphic to G bar, so there's some isomorphism from G to G bar. I'm assuming G bar is isomorphic to G double bar, so there's some other isomorphism from G bar to G double bar. What should I call it? Oh, how about another Greek letter? Phi is this one. How about another one that starts with the F sound? Or actually, it starts with the S sound, but we spell it PSI, psi. That's phi. That's psi, but you spell it PSI. So you got to use this somehow to come up with an isomorphism from G to G double bar. How about composing these isomorphisms? That's the only thing that makes sense to try, right? No, this is a big theme for us, actually. Both in the lectures and in class here, I'll emphasize this a lot. It's a big theme. A lot of times when you're doing these really abstract things, there's only one thing that makes sense to try, and you try it and it works. It's almost like set up to work. That's why I think a lot of abstract math is easier than applied math, because it's like the only thing that makes sense to try actually works. Whereas in applied math, there's like lots of things you can try, and it's not clear whether any of them are going to work. Like think about statistics, like, you know, you've got these different kinds of tests you can do, different kinds of models. Is a normal model appropriate, or is it a t-distribution? You know, it's not clear whether the statistical theory that you do really applies in a given real life situation. Like, and are we even doing random sampling, for example? So applied math, because of that, I feel like is harder. But with pure math, even though it's so abstract, that makes it difficult. Once you get used to the abstraction, you like do the only thing you can do and it works. That's the only thing we can do here, it seems, is compose these things. Psi compose phi. Remember, in function composition, the composition is right to left. It's easy to forget that. So this means apply phi first, then apply psi. So the question is this composition an isomorphism? Certainly it's one-to-one and onto. That's chapter 0, a theorem in chapter 0. You compose two one-to-one functions, you get a one-to-one function. You compose two onto functions, you get an onto function. Certainly the composition psi compose phi is one-to-one and onto. Is it operation preserving? Is it OP? Well, you just got to try and see. What's psi compose phi of a given product AB, where A and B are in G? You have to, first of all, use the definition of function composition. That's the same as psi of phi of AB. And I hope you look at that and say, okay, I've got to use the fact that psi and phi are operation preserving. That's got to be relevant. So first use the fact that phi is operation preserving and write this. Phi is OP. Oh, then use the fact that psi is OP to write this. Get the ordering right here. Psi is OP is the next factor that we use. And does that do it? Yes, it does. This is psi composed phi of A multiplied by psi composed phi of B. That does it. This product A, B is a product in G. This product, and I do mean product, psi composed phi of A times psi composed phi of B. The product there, if I was going to put a dot in there, I'd put it right there, is the product in G double bar. But this verifies that it's operation preserving. Another key thing about really abstract things like this, well, a couple key things, is it's getting at the core reason why things are true. When you do abstract math, you're trying to get at the core reason why things are true. That's really going to hit home, I think, when you take real analysis next fall. I'm thinking in particular of what does it really mean for a function to be continuous? And I don't know if you remember from calculus, but the definition of continuity involves limits, which involves like epsilons and deltas. Maybe you didn't learn about that. Maybe you did. It was kind of confusing. And in real analysis, you relate it to something called open sets. And the concept of an open set is related to the epsilons and deltas. But if you think about it in kind of an abstract way, you get at the core reason, the core idea of what continuity really means. I'm not going to say any more than that because it's too in-depth to get into. But that is what happens in that class. Another good thing about abstraction is that it unifies lots of different things. You can apply it to lots of different things when you do abstract math, like when you do vector space theory and linear algebra. It applies to any vector space. So the result, you don't have to redo results. You can prove results once and for all in the abstract setting, and it applies to lots of situations. So that's another benefit of it. So what do we have here? We've got the reflexive, symmetric, and transitive properties being proved. Therefore, isomorphism does define an equivalence relation on, oh, I made a typo way back there. This is supposed to be a cursive G. An equivalence relation on cursive G. And when you've got an equivalence relation, you should never forget what that means. That implies something that I haven't mentioned. Equivalence relations partition the set. So the fact that isomorphism is an equivalence relation on cursive G, the set of all possible groups, means that it partitions that set into pieces that are disjoint, non-overlapping, and whose union is all of G. That can be quite a significant thing sometimes, especially in group theory here when we start chapter 7 on something called Lagrange's theorem. That's going to be a big, big deal. Is it a big deal here in this example? Theoretically, yes, though it's hard to see any practical applications of it other than just as an idea. Two groups in this collection of all possible groups are going to be in the same equivalence class if and only if they're isomorphic. Okay, is that a big deal? Maybe, maybe not.